Hello everyone, today we'll see how to build a decision tree and which criterions to be used for selecting an attribute for a split. The criterions are namely information gain and Gini index. Information gain is also known as entropy. So these two are the in matrices using which we choose the attribute. Now we'll see how these two are different and if so and if there and what difference does it make in the algorithm and its prediction. So now let us get into what information gain is. So basically this is the formula of information gain, that is summation of negative pi log pi base 2, summation ranging from 1 to c being the number of classes and pi is the probability associated with the ith class. So if there are two classes, there will be p of positive log p of positive base 2 plus log p of negative into log p of negative base 2 whole bracket and minus. So the value of entropy ranges from 0 to 1. So what does 0 mean? 0 means a totally pure split. That means if there are two classes and I have 6 data points, and if all of the data points are assigned to a particular class, then it's a pure split. And what is an impure split? If out of those 6 data points, 3 are assigned to a particular class and the next 3 are assigned to the other class, then it's an impure split. That is a totally random split. So a value of 1 means it is an impure split and not a good split. Now let's come to Gini coefficient or Gini index. So now if you see the formula over here, Gini index is 1 minus summation of p of I whole square ranging from 1 to c. Again, c being the number of classes and pi is the probability associated with the ith class. Now we see this has got no log term with it. So the calculation is less complex or less time consuming because it has no log term in it. So what is the range of value for Gini coefficient or Gini index? It is basically from 0 to 0.5, where 0 means a pure split and 0.5 means an impure split, the same way as it meant for entropy. There's a value of 1 has been replaced by 0.5. So 0.5 means out of 6 data points, and there are two classes, if 3 of them are assigned to a class A and the next 3 are assigned to class B, that means it is an impure split. Whereas 0 means it's a pure split such that all of the 6 data points are assigned to a particular class. Now we all know of overfitting, that is if my algorithm performs very well with my training set but fails to perform that well or fails or underperforms in a testing set, we call it that overfitting. That is, it is a high variance model. So to stop this, we go for pruning, that is we cut the decision tree short and do not let it extend in the entire depth of it. So here are the libraries that we would need. They're all imported. Yes. So the dataset that we'll be using for this is the car evaluation dataset. It is the dimension of is 1728 by 7. These are the top 5 row. Basically, these are the column names actually. That is safety, class, luggage boot space, persons, doors, maintenance, buying, etc. So we'll not be delving much into the data pre-processing steps. We'll just breeze through it and go through directly the model building. Yes, so pre-processing steps are done. I'll attach the link of this notebook in my video in the description box, so you'll get the entire thing and you can check it out for yourself. The notebook also contains the terminologies like pruning, leaf node and the definitions of them, and it will be helpful for you. So as we build the classifier, so first we'll use Gini index. So Gini index, we can choose the Gini index by referring to as Gini in the parameter known as criterion. So we have run it, and over here you have used Gini. So the accuracy for the test set is 0.8021. That's quite a good accuracy. We haven't even done any hyperparameter tuning as of now, so it's good. And this is the test set accuracy. This is the training set accuracy. It is 0.78. So as we see that both the training accuracy and the test accuracy are kind of similar to each other, so we say that there is no overfitting. Had this been a large difference, we would have said there could have been an overfitting, but over here we don't see that. Let us visualize the tree. This is the tree that we have built using the Gini coefficient. As we see, the values are also given in each split, each node. This is just one more way of visualizing the same tree. This is more colorful way actually. Now we move to the decision tree with the criteria and entropy. Again, so in place of Gini coefficient, in place of Gini, we have just used entropy in the criteria parameter or hyperparameter, whatever we say. Now we again check the accuracy is the same. 0.8021, it's same as that of the decision tree in which we have used Gini. So we see that in this particular example, the value or the accuracy of both the training and test are exactly the same. Again, over here training accuracy is again 7865, which was exactly the same as that of Gini. Is exactly the same, and hence again we again see that there is no evidence of overfitting. So what we say is, in this case as well, the value of the accuracy scores and everything are exactly the same as that of the decision tree in which we had used Gini. So how is it same and why? As this is a small data set, the value would not be much different. It might have been so had we used a larger data set, the values might have been different. One thing that we see over here, the time taken for the decision tree with entropy as the hyperparameter is 0.007. Now let us see the time taken for the decision tree with Gini. It's 0.009. We see the time taken for Gini is more than that of the entropy. But our calculation, the formula of Gini doesn't have a log term in it, whereas entropy has. So effectively, Gini should be faster. But over here, it is not. So one reason is, so the only reason over here is, as we are using a third, an online editor, the speed allocation changes from block to block. If we run it again, the speed will again be different. It's 0.005. It changes, but the difference would not be much. Even if it is more or less, the value is very similar. The time taken is very similar among the two. It's very similar. So in case of a small and as it is a small data set, the time difference is not much. But had it been a larger data set, it would have been a large difference. So Gini is faster than that of entropy overall. Again, we see the time is very similar. That's also 0.005, and over here is also same because it's a small data set. So we see how both of these criterions could be used. Now, which one to use when? Well, we can use entropy for a smaller data set, whereas Gini is advisable to be used with a data set which is very large, say millions of rows. In that case, Gini would be a better choice. It will be faster and it will be overall a better criterion to be chosen. I will attach the link of this notebook in my description box, and you will get all the lines of codes and the calculations as well. Thank you. Hope you enjoyed it.